Let's look at the reason why when we add, for example, pentane liquid to octane liquid, we lower the partial pressure of octane in the gas phase. Raoult's law, which says the partial pressure of octane, which of course we can write as the mole fraction of octane times the total pressure in the system, is equal to the mole fraction in the liquid phase of octane times the saturation pressure of octane. So this is Raoult's law. What's a explanation of why this happens? And so let's look at a simplified system that'll make it easier to explain this. So the simplified system is just a dissolved solute. You know that when we add, for example, a salt to water, we lower the vapor pressure of the water of the solvent. So the partial pressure of the solvent is the mole fraction of the solvent times the saturation pressure of the solvent. So by adding a solute, solid, with in this case we'll consider it has no vapor pressure, we're lowering the mole fraction of the solvent, and therefore we're lowering the pressure in the gas phase. Now we're looking at ideal solution, which is what of course is assumed in Raoult's law. So we'll look at that, and it's a pretty good approximation because let's look at the case when XB is on the order of 0.98, so it's mostly solvent. We're adding a small amount of solute. So here's a representation, a simple diagram. We're starting out where we have a solvent, liquid, and vapor in equilibrium. Its pressure then is the saturation pressure. At the same temperature, we add a solute, something with no vapor pressure. Then the pressure we measure is just the pressure of the solvent, but that's going to be less than the saturation pressure. So let's first compare vaporization, and what we're going to look at is comparison on a basis, so it's per mole of solvent that we're going to compare. So we have the heat of vaporization for B, pure component, and over here we also have a heat of vaporization for B. This is for the solvent that is mixed with the solid, but we're looking at evaporating 1 mole of B in both cases. And these are going to be equal if it's an ideal solution, because an ideal solution means delta H of mixing is equal to 0. So now we want to make the same comparison but for entropy instead of enthalpy. So we're looking at entropy increasing this way, and for the pure solvent we have some entropy of vaporization. Now this entropy of vaporization, basically from our definition of entropy, is going to be the enthalpy of vaporization over the saturation temperature to temperature where we're doing the vaporization, where we have vapor liquid equilibrium. So this is the pure solvent case here, and we want to compare it over here to the mixture. And so the entropy for B in the mixture is going to be higher. So this is the liquid solvent that's in the mixture, and this is the entropy of the solvent. So keep in mind, we're looking at entropy per mole of the solvent. And this is higher because we have an entropy of mixing. So even though it's an ideal solutions still have entropies of mixing. So the entropy of the mixture is greater than the entropy of the pure component. That's the entropy, of course, per mole of the mixture, which means the entropy per mole solvent is higher. Now we're going to evaporate a mole of the solvent. This entropy change for vaporization of a mole of solvent is the same because the enthalpy of mixing, right, delta H of mixing is 0. So the energy change is the same, again is equal to heat of vaporization. We just showed earlier that that didn't change. The temperature carrying this out is the same. So that's the same. This now is the vapor of the solvent in the mixture. And so what this simple diagram says is the entropy of B for the solvent, so just for B in the mixture, is greater than the of B as the pure material. And this is for the vapor phase, right? So I'm just comparing this entropy to this entropy. Well, the entropy is higher in the gas phase. The temperature is the same. Both cases, the gas phase is only B in the gas phase. Temperature's fixed, entropy is higher. That means the pressure of B is lower, because at constant temperature, to decrease the entropy of an ideal gas, we lower the pressure. So therefore, that means the pressure B, this is in the mixture, is less than the saturation pressure B. And this is, of course, what Raoult's law says it's lower. and it's going to be lower related to the mole fraction, the liquid phase. And the reason it's lower is just based on an entropy argument. So Raoult's law predicts that adding a salt to a pure material is going to lower the gas phase pressure. The other way we can look at this, it lowers the normal boiling point. We add salt to a liquid phase. And we've explained this based on the fact that we've raised the entropy in the liquid phase. The entropy of vaporization for the solvent is the same. Therefore, we must have raised the entropy in the vapor phase. How we can do that is by lowering the pressure.